topics from the last couple of weeks. So let's say the first one, 40 milliliters of serum is mixed with 120 milliliters of NS. Find the dilution. Remember, in a dilution, my pen will work. What we're looking at is the ratio of serum to total. So it's serum to total. So we have the amount of serum is the 40 milliliters. The total would be, technical difficulties abound today apparently. There we go. So it's 40 milliliters over 40 plus 120 milliliters. So that's 40. The milliliters will cancel out over 160, which reduces to a 1 in 4 dilution. Technically, it would be listed as 1 in 4 like that. If you left it as 1/4, that's okay. Any questions on number 1? Okay. Number 2, a 63% solution is used in a 2 in 9 dilution. What is the concentration after the dilution? A 2 in 9 dilution, the dilution ratio is the same as the ratio of the solution concentrations. So after the dilution, obviously we expect it to be a smaller concentration. So we put the 63 with the larger number, which is the 9. 2 times 63 divided by 9 would be 14%. So after the dilution, we have a 14% solution. And the bottom one here, 240 milliliters of 36% solution is diluted to 9%. How much saline was added? So we've got 36% times 240 milliliters. By the way, this is C1 times V1 equals C2 times V2 that we're using here. So 36% times 240 milliliters equals 9% times V2. So we have to do the 36 times 240, which is 8,640, equals 9 times V2. What's our next step? Divide by 9 gives us 960 equals V2. Now we have to make sure that answers our question. The question was how much saline was added. The 960 is in milliliters, but that is the total volume after it is diluted. So the saline added is 960 minus 240, or 720 milliliters. Any questions on those? Okay, I've got a couple more I want to ask to review. I call this 4. In a 2 in 7 dilution, so in a 2 in 7 dilution, what is the ratio of serum to saline? I'm going to pause, let you guys. Okay, so 2 in 7 dilution, what's the ratio of serum to saline? Well, the 2 in 7 is the ratio of serum to total. So if we want serum to saline, it would be 2 to 5. Perfect. What dilution is required to dilute 72% solution to 27%. So up there, what do we have? Well, our dilution ratio is equal to the after concentration over the before concentration, right? So we have 27 over 72. Now I could reduce those. Both of those can be divided by what? 3 would work. 27 divided by 3 is 9. 72 divided by 3 is 24. Still divide by 3. Gives us a 3 to 8. So it's a 3 and 8 dilution. "360 milliliters of saline is added to 150 milliliters of 24% solution. Find the new concentration." There are actually several ways you could approach this problem. The quickest one is probably the C1V1 equals C2V2. You could have done it brute force through dilutions if you'd wanted to. If we do C1V1 equals C2V2, what is C1? Remember, C1 is concentration, so it has to be a percent. So we'll do it with the 24%. Times, what's the volume then that links with the 24%? 150. The new concentration then is what we're looking for, C2, times the volume is going to be, careful, 360 plus 150. It's been added to it. So we've got 24 times 150 is what, 3,600? Equals C2 times 510. So we divide by 510, which is going to give us 7.059, looks like 7.06 we'll call it. Percent is our new concentration. Any questions? Did anybody take it out brute force using dilutions? Wants to see it done that way? That's one thing, is we can't always go back to dilutions. We know that a 24%, 150 milliliters, well, we have 150 milliliters over 360 plus 150, which of course we know is 510. Unfortunately, you got to remember the 24% is the higher percent, is going to be reduced. So it has to go on bottom. So you can set the ratio of volumes to the ratio of percent. Okay, so we've talked about concentrations a lot in here. We actually started in the last unit dealing with mixture problems, mixing different solutions. So we should talk a little bit about how concentrations are calculated. So we're looking at percent concentrations in solutions. Now, a little note about solutions that we have to keep in mind. When we talk about putting, 30 milliliters of alcohol in 200 milliliter total solution. One of the reasons we do that is volume is not conserved. I'll talk about what that word conserved means in just a second. In solutions. Volume's not conserved in solutions. What that means is if I add 30 milliliters of alcohol plus, let's say, 70 milliliters of water, of saline, we might not get 100 milliliters. Most likely it'll be measurably less than 100 milliliters. The reason for that is the way a solution works. If you have the water that has particles, and everybody thinks water is like fluid and all connected and stuff, but there's actually space between those particles. And alcohol has significantly smaller particles to it. And those particles actually fit in between the gaps, in between the particles of water. So think of it almost like taking a bucket full of normal sized rocks and dumping sand in it. The sand kind of sifts down in between the gaps in the rock, between the rocks. And that's kind of how solutions work. That's why salt goes into solution in water and sugar goes into solution in water, because they fit into those gaps between the particles. So we can't add volumes. The other side of it, however, if I add 30 milligrams of a medication, let's go alcohol, plus 70 milligrams of water, of saline, it will equal 100 milligrams total. Mass, if I get my pen to work, mass is always conserved. I say that kind of tongue-in-cheek. Mass in things that we do, it's going to sound weird, but at the surface of the earth at normal speeds is always conserved. The only time mass is altered is if you go at speeds approaching the speed of light. Hopefully you're not mixing things quite that fast. So when we do our percent solutions, we have to be very careful about saying, well, we added 30 milliliters of alcohol to 70 milliliters of saline, and saying, well, that's a 70% solution then, right? Sorry, not 70%, that's a 30% solution, because it's 30 milliliters of alcohol and 100% total, 100 milliliter total solution. It's not necessarily 100 milliliters total. So one of the types of solution we will talk about is a volume in volume solution. When we talk about a volume in volume solution, the abbreviation is V/V. When we talk about a volume in volume solution, we will always be comparing the volume of the serum or concentrate to total volume. So if we mix 50 milliliters of blood into a 200 milliliter solution, the concentration found would be, well, 50 milliliters of blood is our serum. 200 milliliters is the total solution. Milliliters cancel out, and to make this a percent, we're comparing it to 100. Cross multiply. 50 times 100 divided by 200 is 25. So that's 25 out of 100, or a 25% solution. Now, I realize we've discussed a lot of things here where we said we're going to take 50 microliters of urine and add 150 microliters of saline. Those are both water-based, so that is a true volume plus volume. So it's not always true that they don't add up, but it's better off, like we said, that we take the total solution rather than adding volumes. Okay, so let's look at this. How much serum is needed to create 240 milliliters of 35% solution? I should say 35% volume in volume solution. So volume in volume is going to be serum to total. 35% is 35 out of 100. The 240, what does that represent? Total. We are looking for the amount of serum, so that missing number is what we're looking for. So we do 240 times 35 divided by 100, which gives us perfect, 84 milliliters. They call this one a weight and weight solution, which is a misnomer. It's actually originated back when they used standard units for everything. And when we use standard units, we did use weight and weight. We measured ounces and drams and grains and stuff like that. So it was weight and weight. Now that we use the metric system for everything in the medical fields, it's really mass and mass. It's just they've kept the old label, weight and weight. So it is labeled as W/W. And again, since weight or mass are both conserved, here we don't have to just do so much serum in total. We can actually add the parts together. So let's say find the concentration. If 40 milligrams of serum is mixed with 240 milligrams of NS. Well, in my ratio, it's still going to be serum to what? Total. Very good. It's always serum to total. How much serum do I have? 40. Now, I am not told the total, but I do have the serum and the saline. Am I allowed to add those? Yes, because it is mass or weight, I am allowed to add them. So 40 plus 240 is 280 milligrams. So the milligrams will cancel out. Now on the other side, we're turning it into a percent. So it's out of 100. If we do 40 times 100 divided by 280, it is what, 14.2857143 approximately? We'll call it 14.28%. For percents, yes. Percents are always out of 100. Remember, percent means out of 100. Find the weight and weight concentration of a 400 milligram solution containing 50 milligrams of blood. I'm going to give you a second to do that one on your own quick. So for this one, again, it's always serum to total. On top, how much serum do we have? The 50 milligrams of blood. On bottom, we have 400. 400 milligrams of solution. That's the total solution. So then we have 50 over 400 equals blank over 100. We'll cross multiply and divide. 50 times 100 divided by 400 is 12.5. So that is a 12.5% solution. I'm guessing you got 11.11 if you did the 450. Find the weight and weight concentration if 80 microliters, not microliters, micrograms, I should say. 80 micrograms of serum is in a 10 milliliter solution. There is something a little bit off in this problem. Can anybody tell me what it is? Yep, I said milliliters again. I should have said milligrams. Yes, but it is. Yeah, we did go from micrograms to milligrams. One of them must change. One of the keys to this to make it work is I have to be comparing two things with the same units here. So I either have to make both of them micrograms or both of them milligrams. Probably easier to make both of them micrograms. So the 80 is going to stay 80. Is the 10 the total? In a 10 milligram solution. It is the total. When it says milligrams of solution or milligram solution, that is the total. If it says milligrams of saline or water, that's just the water. Okay. Yep, we'll give you a second. This is a mu. Yeah. Yes. Of saline or of NS is just talking about the saline. Whenever it says in a 10 milligram solution or in 10 milligrams of solution, that is talking about the total solution. So now we have to convert the 10 milligrams into micrograms. Remember, from milli to micro, it's any of our conversions in the metric system are basically 1,000. From grams to milligrams is 1,000. From milligrams to micrograms is 1,000. 10 micrograms is 1,000 milligrams. So 10 milligrams is 1,000 or 10,000 micrograms, I should say. My tongue is not working today either, apparently. So now if we cross multiply and divide here, it is a 0.8% solution, yes. Find the weight and weight concentration if (800 micrograms of blood is mixed with 10 milligrams of saline. Let's get back here. So once again, we do have the issue of different units, milligrams and micrograms. We got to convert one to the other. Which one are we going to go with? We're going to convert everything to micrograms or everything to milligrams? Let's do it each way. In the first one here, we'll go everything to milligrams. So what that means is the 800 micrograms becomes 0.8 milligrams. Does 10 go on the bottom here? No, what goes down there? 10.8. 10 milligrams plus the 0.8 milligrams. Because this is just of saline here. So now if we cross multiply and divide, 0.8 times 100 divided by 10.8. Gives us 7.41%. We would have had the same percent going the other way, by the way. If we changed everything into micrograms, this would have been 800 micrograms. This would have become 10,000 micrograms. So I'd be putting in 10,800 micrograms down here. Cross multiply and divide, and you will still get 7.41. One other type of concentration we want to talk about, and that is a weight in volume concentration. little bit of a review of our metric system before we can make this one work. The definition of 1 gram is the mass of 1 milliliter of water. Of course, remember 1 milliliter equals 1 cubic centimeter. Most of the things that we're going to deal with in medications, in the medical fields, most of those liquids have densities very similar to that of water. So most of the stuff we're going to mix is already actually mostly water in the first place. So we can use this equivalency of 1 gram is equal to 1 milliliter, or compares to 1 milliliter, with pretty much everything we work with. I mean, there are certain things like glycerin that are significantly thicker and more dense, but you also can't mistake viscosity for density either. Things that are more viscous, that are thicker, may not be more dense as well. But anyway, we are going to compare then weight and volume. W/V is the abbreviation. Now again, note that this is mass and volume technically, because grams are mass. The weight of the serum is going to be in grams compared to the volume of total solution in milliliters. Now, the other ones are typically used for mixing liquids into liquids. The weight and weight, or mass and mass, is technically preferred because of that idea that you can add together the masses, they're conserved, whereas the volumes you can't. Weight and volume is typically used when you have a powdered medication being dissolved into a liquid so it can be delivered into the patient. So we might have 20 milligrams of morphine dissolved into 50 milliliters of total solution. Now we have to be very careful here. The weight is always, the mass is always measured in grams. This is now milligrams. So we have to convert 20 milligrams into grams. To get from milligrams to grams on our chart, it is 1,000. It is 3 spots to the left. So we are dividing by 1,000, moving that decimal point 3 spots to the left. So it is 0.02 grams. So the concentration here is 0.02 grams of medication to 50 milliliters of total solution. Equals whatever our percent is out of 100. So 0.02 times 100 divided by 50 is 0.04, yes. That's a 0.04% solution. Morphine's an extremely potent medication, by the way, and it is generally given in very, very small concentrations. 20 milligrams of morphine would kill like 4 people, by the way. You're taking applications for the 4th? How much medication is required to mix 80 milliliters of 30% weight and volume solution? Mass of medication. Okay, so it's the mass of medication over the total. So the mass of medication in grams over the total volume of the solution in milliliters equals 30% is 30 out of 100. So it'll be 80 times 30, which is 2,400, divided by 100 is 24. So that's 24 grams of medication in 80 milliliters. By the way, a weight and volume solution typically has much lower concentrations because you have to dissolve the powder into the liquid, and you can't dissolve large amounts of powder into small amounts of liquid. So 30 milliliters of medication is mixed with 120 milliliters of saline. Find the volume and volume concentration. Yeah. Nothing that you can calculate here. You cannot do it. When you have a volume and volume solution, you have to have the volume of the serum to total volume. You cannot add. I had to do it once. Yeah. So 40 milligrams of, yes. Because when you're dealing with solutions, sometimes they don't add up, especially if you have the medication isn't specified whether it's liquid or powder. You can put 30 milliliters of salt into 200 milliliters of water, and you will not get 230 milliliters because the salt kind of hides between the particles of water. So let's say we have 40 milligrams of serum is mixed with 200 milligrams of saline. Find the weight and weight concentration. This one's almost cruel to ask after the last one because it's the same type of thing, but it's weight and weight. Since it's weight and weight, we can add them, can't we? Sure. So our serum is 40 milligrams. The total, since it's weight and mass, we can add them. Those are conserved. So it's 40 plus 200 to get the total. So when it's volume and volume, you cannot add them together. It's only when it's weight and weight or mass and mass that you can add them together. I won't ever ask you to add them for a volume and volume one on a test, just so you know. This one can be solved. Yeah. No, I said it was cruel to ask after the last one because it looks the same, but this one you can add and the other one you couldn't. Sorry. Yeah, because this is weight and weight, it is okay to add them. I was kind of expecting a couple of you to say, well, we can't add these either, but you can because it's weight and weight. This one was volume and volume. That's why you can't add. When it's well, if you knew the density, like if you said it was 30 milliliters of urine mixed with 120 milliliters of NS, well, urine and saline, they don't have a volume loss when they're mixed together. No, you don't have to know. I will never give you something that doesn't mix, but I want you to be aware that when you're mixing volume and volume, there's a gray area there that you got to be careful. No. I will leave that up to your chemistry side of things to figure out what you can mix and what you can't mix. But I just want you to be aware when it comes to volumes don't necessarily add up. You guys didn't go over solution reductions in chemistry? So anyway, the percent here would be 40 times 100 divided by 240, which is 16.6 or 16.7%. I think you guys need a break. So let's take our break. It's 11:21. Let's come back at 11:31. So for number one, find the weight and weight concentration. So weight and weight means we can add if we have to. Of 20 milligrams of serum mixed into 160 milligrams of solution. Do we need to add them here? No, it's 160 milligrams of solution. That is the total. It doesn't say mixed with, saline. It says mixed into that solution. So when it's worded that way, that is talking about the total solution. So they're both milligrams, so we can cross them off. 20 times 100 divided by 160 is 12.5. So that's a 12.5% solution. Yeah, it would have to say, mixed with, so many milligrams of saline or whatever. Then you would have to add. Number two, how much serum is needed to create 150 milliliters? So the 150 milliliters is representing total solution. 8%, of course, is 8 out of 100. The 150 milliliters goes on bottom. You cross multiply and divide to get 12. 12 what? Whenever it's weight and volume, it's always grams to milliliters. Oh, sorry, there you go. Finally, the last one, 40 milliliters of serum. So that goes on top. is mixed into a 20%, so that's 20 over 100 on the other side. Find the total volume. So you will cross multiply and divide. 40 times 100 divided by 20 is 200 milliliters. There's some subtleties here that you have to pick up on. Because we're just finding the total volume. We're not adding anything. If it asked you to find how much saline, you couldn't figure that out. When you're dealing with volume and volume, you're always dealing with just the serum and the total. The amount of saline, you have to have more information if you want to know the amount of saline. And we don't want to get into percent reductions in solutions or anything like that. Like that when you mix alcohol and water, you have an 8% reduction in total volume. We don't want to get into that type of stuff. No, it's not. You guys would really have to upset me to get me to do that to you. Our next thing we want to talk about, a little bit more of a piercing topic. I amuse myself. That's what matters, right? Syringes. To deal with a syringe, the first thing we have to do is we have to figure out the scale. And to figure out the scale, we need to figure out what the value of each division is. Each division, each space, however you want to refer to it. I'm actually going to decrease my line weight here just a little bit. That'll be better. So let's say this syringe here is numbered as milliliters, 1, 2, 3, 4, like that. What does each space represent? Now, a lot of times on a syringe, the beginning down here towards the tip is tapered, and because of that, the first couple of marks are a little unclear. So we usually go from one numbered space or one numbered marking to another numbered marking. If they're available, we'll go from 1 to 2, which is what we'll do here. From 1 to 2, so that's 2 milliliters minus 1 milliliter, which is a 1 milliliter difference. How many spaces are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, correct? So that's divided by 10 spaces, 10 divisions. 1 milliliter divided by 10 is 0.1 milliliters. So each space, each division on this syringe is 1/10 of a milliliter, or 0.1 milliliters. You see how we found that? So if I fill it up to that line, it's how much? 3.7, very good. This is 3 right here. Each is 0.1, so that's 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. 3.7 milliliters. So to figure out what each division means here, we go from 1 to 2. So that's 2 milliliters minus 1 milliliter. There's a 1 milliliter space. How many spaces are there? There are 5 in between. So 1 milliliter divided by 5 is 0.2 milliliters per division. That's the line it's supposed to line up with. My coloring sucks. What is that? 5.6, good. This is 5 milliliters, and it's 0.2, 0.4, 0.6. If it's whiskey, I'm in. Figure out what each division stands for here. $20. Okay. There's 20 spaces. Because it says milliliter here. So that's 1 milliliter, 2 milliliters. Now, a little trick for, I haven't divided that out yet, I know. A little trick here, though, is you can count 1, 2, 3, 4, 5. So 5, 10, 15, 20, if you want to count it that way. 1 milliliter divided by 20 is 0.05 milliliters per division. So that makes this a little bit trickier to read. So let's say it goes to that one. That is 2.05, 10, 15, 20. Any questions? Figure out what that level on the syringe is. If we go from marked divisions from 0.1 to 0.2, that's a difference of 0.1 milliliters. And there are 10 divisions in between there. So we divide that out. That's 0.01 milliliter, a hundredth of a milliliter per division. So this is 0.3 here. 3.1, 3.2, 3.3, 3.4, 3.5, 6, 7, 8. 0.38. It is milliliters, by the way, not liters. My M just disappeared on me for some reason. I'm thinking funnel. I should fill it for you. So find that level on the syringe. Yes. So when we go from 5 to 10 here, that's a 5 milliliter range. There are 10 divisions in between. So 5 milliliter divided by 10 is 0.5 milliliters per division. So this is 15, 15.5, 16, 16.5 milliliters. Oops, what just happened to me there? So here's the syringe we have. The order is to give 1.8 milliliters. Can we do it with this syringe? Yeah. This is marked in cc's, but we know that cc means cubic centimeter, which means milliliter. They're the same thing. A cc, a cubic centimeter, a milliliter. Well, cc stands for cubic centimeter is where it comes from. But it is a milliliter. 1.8. Tell me where to stop. Right there? This would be 1.5 right here. Yep. From 1 to 2, that's 1 milliliter. There are 20 divisions. So it's 0.05 per division. So this is actually 1.5 here. This would be 1.75, 3/4 of the way. 1 past that. Let's talk about appropriate syringes to use. All of them? Cleanest one? Ouch. Rinse it out a little bit. It's good to go. They've got a good immune system. Okay, well, I'm just a little short of syringes, so I'm cleaning a couple up here. Just washing out. We're going to use the cleanest one. Huh? Sure. Just rinse it out with warm water. That's okay. So here's the order is given to give 1.4 milliliters of medication. Both of these syringes are capable of measuring out 1.4. Which syringe would you use? Why the top one? More precise, what do you mean? Okay. Okay. You've got the picture there. The way these syringes are structured, I mean, I have them drawn out identical on my paper because, well, maybe I'm lazy, I don't know. But this one with the numbers being further apart is probably a much thinner syringe. This one with the numbers closer together is most likely a wider syringe. When you do this, that plunger sliding back and forth, if here's your target amount, that plunger may end up slightly past it or slightly short of it. When you're doing it, you're not going to be perfect. It's not going to end up exactly on that line. Which syringe is that difference going to be less amount of medication? The smaller one, the narrower one. In the wider one, volume is related to a surface area times a distance. Assuming that you're off by the same distance in either syringe, the one with the bigger area, the plunger, is going to be a larger volume for that distance. Does that make sense? So you always want to deal with the syringe that is thinner that can still handle your dosage. You don't want to have to stick them twice if you can avoid it, but a fuller syringe is always more precise. So this one, 1.4, is going to end up being, what, 1, 2, 3, 4, right here. You'd fill it up to there. 1.4 here would be right to there. Which syringe is fuller? The top one. What's that? Which syringe would you use? They are milliliters both, by the way. Why the top one? Yeah, the bottom one isn't big enough. 8.6 is going to be somewhere in here on this syringe. We can't get 8.6 in the bottom one. We don't want to have to give them 2 or 3 shots to get that medication to them. Depends on the patient. They throw their mashed potatoes at them, you're going to stick them 8 times next time. Give me the 1 milliliter one. Okay. True. The moral of the story is you don't want Ashley as your nurse. Okay, so anyway, let's talk about dosages. A little bit of vocabulary we need to clear up before we talk about dosages. The on-hand dose is found on the label of the medication. Examples of on-hand dose. If it's labeled 300 milligram tablets, 300 milligrams is the on-hand dose. If it's labeled often might be labeled 5 milligrams in 20 milliliters. The 5 milligrams is the on-hand dose. The vehicle carries the on-hand dose to the patient. So the vehicle in each of these problems, or each of these examples, the tablet in the first one would be the vehicle. So the on-hand dose of 300 milligrams is carried to the patient in the form of a tablet. In the second example, the 20 milliliters is the vehicle. The 5 milligrams of medication is carried to the patient in the 20 milliliters. Now, there are 3 ways of calculating dosages. One is dosage calculation formula. Not my favorite way of doing it. Partly because it requires you to memorize a formula and to be able to pick out the information and put it in there in certain places, which is fine. But in more complex problems, you have to repeat the formula 2, 3, 4 times to get to the right answer. The second is proportions. I don't mind proportions because proportions, all you're doing is matching things up and cross multiplying and dividing. The weakness of proportions is sometimes it cannot solve the problem in one step. You have to go through multiple steps. The final one is dimensional analysis, which is really nothing more than just our measurement conversions that we talked about. I'll try to withhold bias, but dimensional analysis is by far my favorite method of using. Let's look at the dosage calculation formula. The dosage calculation formula looks like that. D is the desired dose. In other words, that's the doctor's orders. H is the on-hand amount from what we defined up above. V is the vehicle. I'm sensing some negativity back there. A is the administered amount. So how does this work? Let's say the doctor orders 800 milligrams of ibuprofen. Okay. I'm sure I butchered the spelling, but oh well. What's that? IB? That works. Look at the label on the bottle, and it says 200 milligram tablets. So for our formula, what is the desired dose? 800 milligrams. The on-hand dose is 200 milligrams. Now, a little note here, by the way. The desired dose and the on-hand dose must have the same units. If they don't, this formula will not work. You can convert them if you have to. Yes. Times the vehicle is a tablet. 1 tablet. Equals A is what we are looking for. Remember, the vehicle is what carries the on-hand dose into the patient. 200. Yes, A is going to be 4. 800 milligrams divided by 200 milligrams is 4, times 1 tablet is 4 tablets. Watch this example. So, sure. So let's say our order is for 45 milligrams. We don't need to specify what. The vial says, come on now. We'll get back to it here eventually. There we are. There we go. This computer and I are going to part ways at some point really quickly. The vial says 5 milligrams and 20 milliliters. What goes on the top of our little happy little fraction? 45 milligrams is what the doctor orders. That's our desired dose. The on-hand dose, we know it has to be milligrams, so that would be the 5. The vehicle, it takes 20 milliliters to carry that 5 milligrams. So we're going to divide 45 milligrams divided by 5 milligrams. The milligrams cancel out. 45 divided by 5 is 9. Times 20 milliliters is 180 milliliters. If it's tablets or capsules, yes. It'll always be 1, yeah. Like here, it didn't specify 1. It just says 200 milligram tablets, but it's implied that it's 200 milligrams in 1 tablet. Okay. 1 tablet, yeah. The main purpose of the vehicle is to specify the units that are going to be administered. For the proportion, it is often easier to start with the label on the bottle or the vial. In other words, what we're dealing with here is going to be the on-hand dose over the vehicle. On the other side, we will have the desired dose, the doctor's orders, and the amount administered. So let's do these examples. Again, let's say the order is 800 milligrams. The label on the bottle is 200 milligram tablets. So H over V would be 200 milligrams over 1 tablet. Now on the other side, it's real easy to figure out what goes in here because whatever goes here has to be in milligrams, doesn't it? Because in a proportion, these units have to match up. So what's going to go up here? The 800, which is the desired dose. Before we cross multiply and divide, what unit is going to be down here? Tablets. So then we will cross multiply and divide. 1 tablet times 800 milligrams divided by is 800 milligram tablets divided by 200 milligrams is just 4 tablets. The formula? The dimensional analysis is so much easier once we get there. Think I'm lying? You like the formula? It's just measurement conversions. It's really, the units tell you what to do. So the order is 45 milligrams. The vial was 5 milligrams and 20 milliliters. So we set it up. It's 5 milligrams in 20 milliliters. Always off the label first. What's going to go on the other side? 45 has to go on top because it's milligrams. What's the bottom going to be? Milliliters. And yes, we cross multiply and divide. 20 times 45 divided by 5 gives us 180 milliliters. Dimensional analysis takes a second to get used to. The power of dimensional analysis is that it can be used for any problem. And what it basically, the key to dimensional analysis is the label of the bottle or vial basically becomes a conversion factor. We will start with the doctor's order and convert it into what we need to administer to the patient. So let's look at our example again. Ordered 800 milligrams. The label on the bottle, 200 milligram tablets. So we start out with the doctor's orders, 800 milligrams. Just like we did with our measurements, we make it a fraction by putting it over 1. The label becomes a conversion factor for us. 200 milligram tablets is saying that 200 milligrams equals 1 tablet. So over here, we want to get rid of milligrams. Notice this is multiply, not equals. In the proportion, that was an equal sign. That's why we could cross multiply and divide. Here, we're actually just multiplying by a fraction or a conversion factor. We're getting rid of milligrams, so milligrams will go on bottom. Going into tablets, so tablets go on top. 1 tablet equals 200 milligrams. The milligrams cross cancel out. 800 times 1 tablet is 800 tablets. 1 times 200 is 200. That divides out. Be 4 tablets. Now I realize, like I said, this takes a little bit to get used to, but the power of dimensional analysis is you're always just starting out with what the doctor orders, and you're converting it into what you administer. And you don't need to know any formulas. You don't have to memorize any formulas. The units tell you what to do. We're starting with milligrams, so to get rid of them, you got to put milligrams on bottom. Let's look at our other example. So the order was for 45 milligrams. The label on the vial was 5 milligrams and 20 milliliters. Again, this label on the bottle is giving me an equivalency that 5 milligrams of medication is equal to 20 milliliters of that solution. So we start out with the doctor's order, which is 45 milligrams, put it over 1. Then, yes, I always put the labels in first just because that's how my mind works. The milligrams will go on bottom, so we're going to go to milliliters. Yes, 20 milliliters over 5 milligrams is what it ends up being. And you can see the milligrams cancel out. 45 times 20 milliliters is 900 milliliters. 1 times 5 is 5. 900 divided by 5 is 180 milliliters. This process works with just about anything. For example, let's say your bottle says 4 milligrams per kilogram for the patient. You have a patient that comes in weighing 42 kilograms. (42 kilograms over 1. Kilograms on bottom, we're going to milligrams. 4 milligrams to 1 kilogram. (42 times 4 is 168 milligrams over 1. So that patient should receive 168 milligrams. This is not a problem that would apply to your dosage calculation formula, but you can still use dimensional analysis to solve it. Let's say you have an IV drip. Oops, I don't know why I put a colon in there. So you have an IV drip that needs to go at 4 milliliters per minute. You have a drop factor, 12 drops per milliliter. Your infuser that you're looking at requires you to program it in drops per minute. So you're going to take your 4 milliliters per minute, is going to become 4 milliliters over 1 minute. You're getting rid of milliliters, so milliliters have to go on bottom. You're changing it to drops. Bless you. 12 drops equals 1 milliliter. The milliliters cancel out. 4 times 12 drops is 48 drops. 1 minute times 1 is still 1 minute. That is 48 drops per minute. So as I said, dimensional analysis looks a little awkward at first, but the power of it is just incredible for what you can use it with. We will talk way more about dosage calculations next week. For now, in your book, page 146, 1 through 17, the odds. Page 153 through 154, the 1 through 15 there, that is the vocabulary that we talked about last week. I will not test you on this, but it would be good for you to know it because the vocabulary will appear in the problem, so understanding what it means is important. Page 162 to 163 talks briefly about dosage calculation formula. They're focusing on the formula right now. You can use any of the 3 methods you want to. And then finally, page 168 and 169 is the syringes. That is the end of our time. So you guys have a great weekend, and we'll see you next week.